Welcome to the 21st lecture on CVT, complex variables and transforms, and in this lecture we are going to study inverse Laplace transforms. In our last few lectures we studied the Laplace transform, but in this lecture we'll study inverse Laplace transforms. This means that we will be given f of s, the Laplace transform of a signal, and the target would be to obtain f of t from it, the time domain signal back. Right. So before this we have studied Laplace transform is written as Laplace transform of f of t, and the resulting signal in the s domain, the Laplace domain, we call it capital F of s. This Laplace to the minus 1 means inverse Laplace transform. So this is for inverse Laplace transform. So this is inverse Laplace transform. So given this expression that we already know, if we apply inverse Laplace transform, this means the inverse Laplace transform of f of s, and if we apply inverse Laplace transform on the Laplace transform, this would give us f of t back, because Laplace inverse of Laplace means the original signal f of t. So f of t is Laplace inverse of the f of s, the s domain signal, the signal in the Laplace domain. Right. So having studied this, let's solve a very simple example where we are given these three fractions: 1 over s plus 1 plus s over s squared plus 4 plus 3 over s squared plus 9. We know that e to the minus t, and before this we know that Laplace transform is a linear operator. If Laplace transform is linear, its inverse is also linear. So inverse Laplace transform is also linear. So Laplace transform is linear, inverse Laplace transform is also linear. Therefore Laplace inverse of these three terms being added together can be separated because the transform is linear. So Laplace transform, inverse Laplace of the first term plus inverse Laplace transform of the second term plus inverse Laplace transform of the third term. So this means f of t is, we know that e to the t has a Laplace transform 1 over s minus 1, or e to the at has a Laplace transform 1 over s minus a. We know the Laplace transforms. We have already studied many Laplace transforms before this. Laplace transform CVT, Laplace tables. Right, we have Laplace table here. The Laplace of e to the at is 1 over s minus a. You know that the Laplace of e to the at is 1 over s minus a. If we have a is equal to 1, this is 1 over s minus a, and if it is negative at, this is 1 over s plus a. So if it is negative, e to the minus t is 1 over s plus 1. 1 over s plus 1, or in other words 1 over s plus 1 has an inverse Laplace transform e to the minus t. And we know that s over s squared plus 4. Let's see what it is. S over s squared plus omega squared is the Laplace transform of cos omega t. If we have omega is equal to 2, that would be s over s squared plus 4. That is exactly what we have here, s over s squared plus 4. So this 4 can be written as 2 squared. So omega is 2. This is cos omega t, or cos 2t. Right, and this is 3 over s squared plus 9. Let's see what it is. Sine omega t is omega over s squared plus omega squared. So is omega, if you put omega is equal to 3, that would be 3 over s squared plus 3 squared. 3 over s squared plus 9. 3 over s squared plus 9 is the Laplace transform of sine 3t. This u of t means all this signal, this whole signal, it starts from 1, because u of t is a signal like this. it is 1 for all values of t greater than or equal to 0, but is 0 for all other values. So this is u of t. So u of t means that all these signals starts from 0 onwards. Right, another example is, it's a bit trickier, because now we have, instead of 1 over s plus 1 over s plus 1, we have 1 over s multiplied by s plus 1. Now we know the Laplace inverse of 1 over s is 1 u of t, and Laplace inverse of 1 over s plus 1 is e to the minus t. But it isn't like this, it is not like this, a 1 over s plus 1 over s plus 1. It cannot be written like this. It cannot be written like this, because they are being multiplied together. For that, we'll have to go back to the school and college where we studied a very important mathematical technique that we call partial fraction. We studied in either in school or college partial fraction. Partial fraction means that given this expression 1 over s times s plus 1, we can write it as a over s plus b over s plus 1. This is what we studied in school and college. So the rest of the things are very simple, because now we are going to compute the LCM of the two s times s plus 1. S plus 1 is multiplied by a, b is multiplied by s, and a times s plus a plus b times s. Now we see the both numerators, these two fractions are equal, and the numerators are also the same. If the denominators are also the same. I'm sorry, not numerators, denominators are also the same. So fractions are same, denominators are same. So if two fractions are equal, their denominators are also the same. This means their numerators are also equal. So therefore, actually what we have done here, we have written their numerators to be equal to each other, this numerator and this numerator. And then if we compare coefficients of s, that would be a plus b on the right hand side, and the coefficient of s on the left hand side is 0. So therefore 0 is equal to a plus b, or a plus b is equal to 0. And then we compare coefficients of s naught, or constants. Here we have 1 as a constant, and here we have a. So a is equal to 1. And if we plug a is equal to 1 here, then b comes out to be minus 1. So b is minus 1. So now we have computed a and b. Therefore a is 1, b is negative 1. So if we plug these values here, we can segregate this as 1 over s minus 1 over s plus 1. Now we are in a very good position to apply inverse Laplace transform and exploit the linearity property. Laplace transform of 1 over s, inverse Laplace transform of 1 over s minus minus 1 over s plus 1 is Laplace inverse of 1 over s minus Laplace inverse of 1 over s plus 1. And we know Laplace inverse of 1 over s is u of t, or 1 times u of t. Laplace inverse of 1 over s plus 1 is e to the minus t. So this is how we can compute, with the help of partial fraction, we can compute the inverse Laplace transform, and we can plot it like this. Right, that's all for this lecture. Thank you.